Vibration analysis, diagnosing unbalance, techniques for identifying and analyzing system imbalances. Understanding unbalance in rotating machinery, diagnosing unbalance, agenda, introduction to unbalance. Unbalance in rotating machinery is one of the most common and impactful faults encountered in industrial environments. This presentation introduces the engineering principles, diagnostic approaches, and international standards associated with identifying and correcting mass unbalance. The material is based on vibration analysis knowledge, framed to support predictive maintenance programs and reliability engineering initiatives. Within this context, unbalance is defined as a condition where the rotor's mass center does not coincide with its geometric center, producing a centrifugal force when spinning. This force leads to elevated vibration, reduced machine efficiency, and accelerated wear. Understanding the types of unbalance, static, couple, and dynamic, is essential for performing accurate diagnostics and proper balancing procedures. Additionally, the presentation highlights best practices in field assessment, correction methods, and compliance with standards such as ISO 1940, ISO 7919, ISO 10816, and ISO 14694. Each section will guide engineers through identifying symptoms, analyzing vibration signatures, interpreting phase relationships, and implementing corrective actions, forming a comprehensive view of unbalance management. This presentation follows a structured flow covering all essential engineering aspects of unbalance analysis. It begins with core definitions and physical principles, followed by a segmentation of unbalance types and their vibration signatures. Next, it addresses the root causes of unbalance and how these relate to maintenance practices and operational environments. The agenda continues with the severity assessment methodologies based on international ISO standards, providing the engineer with a robust framework for classification. Real-world diagnostic techniques are then covered, including amplitude and phase interpretation, coast-down tests, and bump testing. Subsequent slides address balancing techniques, safety considerations, and best practices. Case studies and diagram placeholders support visual comprehension, and the session concludes with key summaries and final recommendations. Unbalance occurs when the rotor mass distribution is uneven, causing a misalignment between the mass centerline and the rotational axis. This misalignment generates a centrifugal force proportional to the square of the rotational speed, making unbalance particularly problematic at higher operating speeds. The phenomenon leads to increased radial loading on bearings, structural resonance excitation, and adverse dynamic responses. Engineers must understand that unbalance can stem from manufacturing tolerances, material density variations, operational wear, or external contamination. Detection generally involves observing sinusoidal vibration signatures at 1 times running speed, typically accompanied by a stable phase angle. This foundational understanding sets the stage for deeper diagnostic investigations in subsequent slides. ISO 1940 Overview, ISO 7919 or ISO 10816 Overview, ISO 14694 Overview. ISO 1940 provides guidelines for balancing quality grades related to rotor type and operating speed. This standard allows engineers to classify acceptable levels of residual unbalance in rotors prior to installation. The standard uses a G-value system representing permissible unbalance per unit rotor weight. Higher precision rotors such as turbine spindles require low G-values, while general-purpose machinery may tolerate higher ones. Applying ISO 1940 ensures consistent rotor quality and reduces the potential for excessive operational vibration. Understanding the standard helps engineers evaluate whether a rotor requires shop balancing, field balancing, or further inspection. ISO 7919 and ISO 10816 define criteria for vibration severity evaluation in rotating machinery. ISO 7919 focuses on shaft vibration measurements, generally using proximity probes to measure relative motion. ISO 10816 evaluates casing vibration using accelerometers or velocity probes. These standards categorize machinery into classes based on size, power rating, and foundation type. Each class has predefined severity zones, from acceptable to dangerous, allowing engineers to determine the risk level associated with observed vibration levels. The standards complement each other by providing a comprehensive perspective on rotor and housing vibration behavior, guiding reliable and safe operation. ISO 14694 addresses mechanical vibration in fans, providing limits and guidelines for assessing operational vibration severity. The standard categorizes fans by type, mounting arrangement, and operational power. Engineers use this standard to evaluate unbalance-related vibration, ensuring fans meet safety and reliability expectations. Since fans often accumulate dust or suffer from blade wear, ISO 14694 is especially relevant in ventilation, HVAC, and industrial process applications where dynamic balance conditions can shift over time. Using the standard ensures compliance while preventing premature component failures due to unbalance. Static, couple, and dynamic unbalance, causes of unbalance. Unbalance manifests in three fundamental forms: static, couple, and dynamic. Static unbalance occurs when the mass centerline is offset parallel to the rotational axis, producing a single-plane correction requirement. Couple unbalance arises when equal masses on opposite sides of the rotor produce counteracting forces, requiring two-plane correction. Dynamic unbalance combines aspects of both and represents the most complex form, commonly found in long or flexible rotors. Engineers diagnose these using vibration amplitude and phase readings collected at multiple bearing locations. Understanding the differences ensures that the correct balancing method, single-plane or two-plane, is selected and applied effectively. Unbalance can originate from manufacturing tolerances, uneven material density, machining errors, thermal distortion, corrosion, erosion, dirt accumulation, or operational wear. Overhung rotors are especially susceptible because added mass buildup has a greater effect at the free end. During operation, blade damage, missing fasteners, or partial material loss can rapidly create severe unbalance. Increasing machine speed amplifies these effects quadratically due to centrifugal force dynamics. Engineers must routinely inspect rotors for cleanliness, damage, and dimensional accuracy to prevent unbalance-related failures. Diagnosing mass unbalance, balancing approaches, balancing safety, and good practice. Mass unbalance diagnostics typically rely on observing a dominant 1x running speed vibration peak, stable phase readings, and consistent directional behavior across operating conditions. Engineers use tools such as coast-down tests, influence coefficient balancing, and vector analysis to verify unbalance. Phase measurements are especially critical, as they help differentiate unbalance from misalignment or looseness. In multi-bearing systems, comparing vibration phase between bearings reveals whether the unbalance is static, couple, or dynamic. Correct interpretation ensures proper corrective action without unnecessary maintenance. Balancing involves adding or removing mass to restore the rotor's mass centerline to the rotational axis. Single-plane balancing is used for rigid rotors operating below their first critical speed, while two-plane balancing is required for longer or flexible rotors. Field balancing follows a structured process: measure baseline vibration, add trial weight, record response, calculate correction vector, and apply final weight. Engineers must ensure safety throughout the process by securing components, verifying trial weight integrity, and avoiding overspeeding. Proper balancing significantly enhances machine longevity and reliability. Balancing work requires strict adherence to safety procedures due to risks related to rotating components, unsecured weights, and potential overspeed conditions. Engineers must verify rotor cleanliness, use calibrated instruments, and ensure trial weights are firmly attached. While adding correction masses, maintaining symmetry, and avoiding interference with rotating elements are essential. Proper documentation, including weight placement diagrams and final vibration signatures, ensures repeatability and regulatory compliance. Applying these practices prevents accidents and ensures high-quality balancing results. Summary of key points, references. This presentation reviewed the engineering foundation of rotor unbalance, its causes, types, detection techniques, and corrective methods. Unbalance remains one of the primary contributors to elevated vibration and mechanical wear in rotating machinery. Engineers equipped with knowledge of standards, diagnostic techniques, and balancing methods can effectively maintain machinery reliability and avoid unnecessary downtime. Understanding vibration signatures, particularly the 1x running speed component and phase behavior, is essential for accurate diagnosis. Proper balancing, supported by safety and documentation protocols, ensures compliance and long-term operational stability. References for this presentation include general engineering vibration texts, ISO standard descriptions, and non-copyrighted diagrams. Where applicable, placeholders are included for diagrams that the user can later replace with officially licensed images. These references serve as guidance for further study in unbalanced diagnostics and vibration analysis.